So that's 2D moments. So are we good with that? But of course, we've got a three-dimensional world, so sometimes we have 3D moments that we have to consider. So if you look at that traco there picking up that chunk of concrete, that's going to require a three-dimensional moment to do it. I mean, hard to tell exactly what the traco is doing there, but I think it's going to twist it like that. So hard to draw this, but it'd be like a moment vector kind of coming off that way. The moment vector is the axle about which that 3D moment would turn. Okay. So now I'm on page 270. So a 3D moment about a force has three components. The twist about a line through the point and parallel to the x-axis, which is the I moment. About the parallel to twist about a line through the point and parallel to the y-axis is the J moment. And twist about a line through the point and parallel to the z-axis is a K moment. To determine the signs, you use the right-hand rule. Twist your fingers in the right of the right hand in the direction of the moment. Look at the direction your thumb points. So we're going to break 3D moments down into vectors with I, J, and K components. That's what we're going to do, okay? All right, so let's have a look at these two forces here, and let's find their x components about point A in each case. So what you want to do then is find the twist of that force about a line through A. The line through A would be parallel to the x-axis. Okay? And that would get you the x component of moment. So what we want then is to combine a force and a distance to get that component of moment, and that would be the I moment, and then use the right-hand rule to figure out the sign. We're on page 270 is where we're at. All right, so this first one is a Z force, right? And then what would the moment arm be if I'm going about that dashed line that goes through A? Be 4 meters, right? Good. All right, now that, if you think about that, think of this as being like a levered arm that goes out from that dashed line to the force. That force would kind of rotate about like that. You with me there? Up and over. Now, if you take your right hand and you twist it that way, your thumb points out of the page. Okay, so that's going to be a positive. Okay, so right hand rule. And if you look at that, that is a counterclockwise twist, and your thumb's going to point out of the page. Okay, so that's going to be a positive, and you'll take the 300 newtons times the 4 meters. All right, and what you're going to get there for MAX is positive 1,200 Newton meters. Okay, so that'll be positive there. Now, one thing I'll point out to you is between the three things we just discussed, we get all three axes, because we've got a Y moment arm. Get this zoom put where I want to. There we go. We've got a Y moment arm, we've got a Z force, and we get an X moment. So that's X, Y, and Z. And these three elements always combine to cover all three axes. So a Z force of the Y moment arm will get you an X moment. An X force of the Y moment arm would get you a Z moment. It always covers all three axes, X, Y, and Z. How about the other one there? 600 newtons. Okay, figure out the sign on that. Everyone just have a look at it and figure it out on your own there for a second. We always like to see if we can figure this stuff out and visualize it. Okay, that force is going down. Z force again. Y moment arm. What's the sign on that one? Yeah, see, that's coming around like that, right? Again, think of like if you know what a ball and socket joint is, kind of a cup with a ball in it, kind of like your hip is a ball and socket joint, extending out to where that force is, that thing would be twisted underneath and then up around the other side. Roll your right hand fingers that way, your thumb points into the page. Now, that's negative. Okay. So that would be negative 1800 Newton meters. So that's how we figure up three-dimensional moments. Questions on that? Okay. So if we're going to do this for a full 3D force and a full 3D moment arm, we have to take the force and break it into X, Y, and Z components, and we take the moment arm and break it into X, Y, and Z components, and then we combine them to get the 3D moment. So I've got an example of this. Now, this is on the next page, 280, thanks. Okay, now I'm going to just kind of tell you what's going to happen here. First thing we're going to do is we're going to do this first one visually, which, as I've mentioned, some of you will find more challenging than others, because that's the basic idea of what a 3D moment is. Then I'm going to show you a nice little mathematical tool called a cross product that will do this for us automatically. So it's good if you can visualize this, but if you can't, don't worry about it. We got a mathematical model that will do this for us if we need to. But let's start by doing one visually here. So what I've got there is a 600 Newton force that goes from B to C. I've got coordinates because I've got a rectangular box there. I've got the connection there at A, so I'm going to take moments about A over there. And I've got this force that goes from B to C, like that. I've got the magnitude of the force. And then I've got the dimensions of the box here. I've got the coordinate of B. It's 0.4, 0.7, and 0. Okay. So that's what I've got. I've got coordinates on all these points. I've got RA, 0.40, 0.2, RC, 0, 0.2. All right, so that's what I want to do here is find the moment of that force about point A. All right, now what I do first is get a force vector. All right, and I've got that on the left. And this is something that, we've done a number of times in class. And frankly, you should now know how to do this. This should be a process that you have pretty well figured out. Okay, so RBC is RC minus RB. So I switch the order of the letters. I take RC, which is 0.2, and I subtract off RB. So that will get me the vector that goes from B to C. I get negative 0.4, negative 0.7, 0.2. I take the square root of sum of the squares, and I get the magnitude of the force, which is the length of the line. I divide through by the magnitude of the force, and I get a unit vector. And then I scale the unit vector up by the force magnitude, 600, and that gets me the force that goes from B to C. So step, 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 just walk through that. I mean, we've done that a few times. That's a pretty standard thing to do in 3D. So we good with that? Doing all right? All right, that's over there on the left-hand side. All right, now, if we're good with that, we want to find the moment about A. Now, to do that, we're going to find moment arms from A to any point on the line of action of the force, okay? So the easiest way to do it would be to go to point C. I think that's the quickest and easiest way. I can take any way from A to C I want. I could go to B or I could go to C. I'm going to go to C because it's easier. So I'm going to use that as my moment arm from A to C. And then I'm going to put my force there. Now what I'm doing here is it's easier to visualize if I put the force in three components. So I've got them listed there. 506 in the negative y, 144 I think it is in the z, and 289 in the x, negative 289. So negative 506 for the y. Is that 194 or 144? I'm not sure. 144 in the z and 289 negative in the x. So let's figure out how that causes a moment about A. All right. So let's look at the 144. What does the 144 do about point A? Let's start with that. For starters, what's the moment arm for the 144 Newton force? From there to A. Yeah, point 4. Okay. Now, if I take a rod and I start at A and I connect it to C, how will that rod spin if I apply the 144 to it? What axis will it spin parallel to? Around, I guess would be the way to say. Okay. The distance is an x distance. The force is a z. So how will that rod spin if I apply that force to the rod? Yeah, it's going to come up, and boy, I didn't draw that quite right. It's tough for me to do this in a 2D piece of paper. Something like that. It's going to spin about a y-axis, isn't it? You okay with what I'm doing there? Seeing what's going to happen there? That's going to spin up and over A. It's going to go like that. Yeah. Okay. Positive y-axis by right-hand rule.
Wait, so how do you do the right-hand rule again?
Use your fingers.
Okay.
Turn them in the direction of the spinning. Your thumb then points in the direction of the vector.
So you start from point A, and then you go to C.
Yeah, lay your hand out like that and then spin your fingers in the direction of the moment.
And counterclockwise is positive and clockwise is negative.
Yeah, you look at which direction your thumb points. My thumb points in the positive y direction when I do that. Okay?
But why is your hand faced up?
Okay, so was I faced my hand up because I was kind of looking ahead to see what I had to do with my fingers. I can't curl my fingers down, only up. So I'm going to curl them up like that. So I knew they was going to go up, so I laid my hand flat.
Okay. And you're going up because it's the positive z direction?
Yeah, that force is pushing my fingertips up, and it kind of curls out around.
Yeah.
Everybody all right with that? Okay. All right, so that's what the 144 does. How about the 506? What's it up to? What's the moment arm on the 506? We're going to A, though.
Yeah. 0.4, yeah, the 0.4.
0.4, because we're going from there to A. Now, think of that as being a rod that extends out, and think of there being like a ball and socket joint. You have some of those on the suspension in your car. Your hip's a ball and socket. It kind of allows the rod to go any way, which way it wants. And you push on that thing with the 506. How's that rod going to spin?
When you pull in the 506, it's going negative, right?
Yeah, 506 is going to shown in the proper direction. Just think about it for a second.
So the whole thing will spin to the counterclockwise direction.
Yeah, okay. So, tell physical, right? They're looking at it down. Yeah. So what we got going on is, see, that thing's going to wrap around like that, isn't it? And if you turn your fingers that way, you're going to get a positive. So that'll be a positive z, okay? So that's a k vector. Good, okay. How about the 289? What's that going to do? How's it directed, the 289? Right through the point. That's nothing, okay? So it doesn't do anything. Okay, because the 289 pushes right through the point. Each of the other two forces cause only one component of moment. So the 144 was a z force. The moment arm was in the x direction, so that got us a y component, which is j, okay? The 506 is a y force. The moment arm again in the x direction, so that got us a z, which is a k component of moment. All right? So that's how you compute 3D moments. That's the fundamental idea of how you do it. All right. So when you run those numbers, you get 0i plus 57.6J plus 202K. The units on that are Newton meters because they're a moment. Now that vector that you see actually does represent something. So let's have a look at what that represents. But there's no I, okay? There's just J and K. So if you sketch that vector up, you're going to get an idea of the axle about which that force would rotate about. All right. So there's the directions that those two forces act, as we were just showing. Okay, that's the meaning of a J vector, which I'm showing with the yellow highlighter that goes up and over, and the K vector, which I'm showing with the green highlighter, which comes horizontally in the horizontal plane and around. Okay. Now I can write that up, show that as a vector, okay? And the way I would do that is I would proportion in a vector that's 57.6 in the Y direction for J, 202 in the K. Now, of course, all I'm doing here is sketching on a flat piece of paper, so this isn't going to be perfect. But that's the idea. And what I noticed there is the ratio between Y and Z there, J and K, was about 4-to-1, something like that, 1-to-4. So I made it a lot steeper up in the Z direction than I did in the Y. That was my thinking on that. That is a vector. That's the moment vector. Think about the vector, about the moment twist being a wheel. So if I have this force and it's like a rocket and it's joined to A with a rope, it's going to swing around in the direction that I sketched there as well as I could. Think of that as being a wheel. Your thumb then, the axle of that wheel would be the moment vector, going up that way. That's what that represents. Okay? So that's how we model vectors in 3 space. So that's how I would visualize that. We got any questions on any of that stuff? We good? Okay. All right. Now that was kind of a starter one, okay? Let's do one more visually, but let's not hang up on this too much because like I say, there's a nice mathematical model we can do that will do this for us. But let's just look at one other because, you know, it just depends what kind of engineering you're in. If you're civil or mechanical type, you got to see stuff. You know, this is a good exercise because when you're building stuff, you got to see. If I'm a civil engineer, if I'm doing stuff, I got to see the ground. I got to see what I'm doing out there. You know, I want to develop that ability to visualize. Same thing if you're mechanical. Okay, you want to be able to see the parts that you're designing. Let's kind of visualize this a little bit. Let's put the force at B this time. It's going to be a more difficult location, a little bit more complex, but let's do that. So instead of at C, I'm going to put the force at B. See, I can put it anywhere I want. It's easier at C, but let's do it at B now just to illustrate what's going on here. All right. So let's figure out how we're going to get moments about A. Now this might be a little bit different visualization. Let's start with the 289. What type of moment would the 289 cause about A? There's 2 of them actually. What's one of them? X. I don't know if we got an X on that. I think we've got, actually we don't have an X. We got the other 2. We remember the moment arm doesn't go in the direction of the moment. They're different, okay? Okay, how about this? How about if that front plate, if I think of that as being like a door, a plate? Yeah, what if I put hinges right there? I'm going to have a 0.7 meter moment arm. What type of moment would that cause if I've got hinges right there on that door? How's that door going to swing if I apply that 289 to it?
Around the Z-axis.
Yeah, it's a Z, so that's a K. And again, we have kind of that rule. We got an X force, a Y moment arm, so that leaves Z for the moment. Okay, y'all okay with that? Now, where else can I put hinges? What if I apply that 289, but this time I put hinges up here? What am I going to have with that? Yeah, it's going to swing around. I'm going to have a 289, and what's the moment arm on that one? It's a J, yeah. What's the moment arm? 0.2 meters, and it's a J. What's the sign on both of these? If you swing around the hinges. Yeah, they're positive. Yep. Okay. They're both positive. Because this one's going to come around that way, and this will turn into a mess here, but that's going to be a positive K when I swing my fingers that way. The other will swing around like that, around that line parallel to the y-axis. That'll be positive 2. All right. How about the 506? What's that going to do? It's under A, though. It looks like it's pointed at A, but it's not. See, it's going under. Yeah, and then what kind of moment will that be? So that'll be 506. 0.2 meters, right? That'll be the moment arm along that red line. So the moment arm's right there, 0.2 meters. You all okay with that? That's going to cut under. What type of, that'll be an I moment? And what's the sign on that? Yeah, it's negative, okay, because that's going to swing around like that. Okay, we got one more. It's the 144. Yeah, right. That's times 0.7 meters. I'm running out of room here. I didn't quite space that properly. So that's going to be 144 newtons. Sorry about that. Times 0.7 meters. That is going to be an X, so that'll be an I. And what's the moment arm on this one going to be as it comes around like that? And be positive, yeah. And that'll be an I. Sorry about the writing on that, not the best. There we go. So 506 times 0.2 I negative and plus 144 times 0.7 I, and that'll be positive. So why don't I write that a little bigger here? I just kind of ran out of room. So that's plus 144 newtons times 0.7 meters. Okay, there we go. All right. There you go. Combine everything together. I get a little bit of rounding error in here, but that's just rounding error. That's all it is. See, I get the same answer as I got last time. I combined different numbers together, but I got the same answer. So the point is, you can draw a vector from A to either point on the line of action of that force. You can go out to C, or you can go to B. Either place, you'll get the same answer when you run the numbers. Okay. Now, that's a little bit of an exercise. I mean, that makes you kind of squint and look at something and visualize it. That's a little bit difficult sometimes. So luckily, the mathematicians have come to our rescue. They have developed a nice model for this, and they developed it long before we needed it for 3D moments, I think, but we can use it. So let's have a look at that next, okay? Are we good with this bit first? Are we okay? All right, we good? And what the mathematicians developed for some reason, and I honestly don't even know why they did this, but they came up with something called a cross product. Cross product is another vector operation. It is A crossed with B will get you a vector C. So when you cross two vectors, the magnitude of a cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between them, which we'll call theta. Theta is the angle between A and B. Okay? C is by definition normal to the plane formed by A and B, and the right-hand rule determines the direction of C. So if I take my fingers and point them in the direction of A, curl them towards B, my thumb points in the direction of C. Now, if you're in Math 254, you might have run across this. I don't know if you've got to it yet. If you're not in Math 254, don't worry about it. We'll cover it here, and we'll put a formula for you on the formula sheet, okay? So you're going to have what you need to do this. This is going to help us do moments. It's going to be very helpful. All right? Now, this is based on AB, which is the magnitude of A times the magnitude of B times the sine of the angle between them. So if we start crossing unit vectors, we're crossing vectors that are the same. They're parallel. They have 0 degrees between them, so the cross of two like vectors is 0. They zero out. When you cross unlike vectors together, their magnitudes are 1, and the angle between them is 90. Sine of 90 is also 1. So you get a vector with magnitude 1 that is then the third unit vector. So what I mean by that is if I take I, which would be the x unit vector, so this would be I, if I cross it with j, which would be the unit vector for the y-axis, take my fingers in the I direction, curl them towards j, my thumb points in the z direction, which would be the k unit vector. And that is on the z-axis. So I dotted with j is k. Because the magnitude of I is 1, the magnitude of j is 1, the sine of 90 degrees between I and j is also 1. So when I multiply all that AB sine theta stuff together, I get 1. And by the right-hand rule, I get a k unit vector. If I can run through this for all of them, if I cross I with k, that'll curl my fingers from the x-axis up towards k, all at point in the negative j direction. If I cross j with k, or excuse me, j with I, my thumb will point down in the negative k direction. If I cross j with k, my thumb will point in the positive x direction. If I cross k with I, so that's the z-axis towards the x-axis, my right thumb will point in the positive j direction. And then if I crossed k with j, which is z towards y, my thumb will point in the negative x direction. So there you go. That's what happens when you cross unit vectors, every possible combination of unit vectors. So if I'm going to cross A with B, what I'm going to do, I'm going to use the distributive law and cross every component with A with every component of B. Okay? So I'll cross AX and BX, I dot A will zero out. AX and BY, I'll have I crossed with J, that'll get me K. AX BZ will get me I crossed with K, which will be a negative J times AX BZ. And you can kind of see what's happening there. I'm just working through that where I've distributed everything out, and I'm crossing every possible component of A with every possible component of B. Okay. And then I cross the unit vectors together and get the stuff that I derived up above. Okay. So what I end up with if I collect terms is this equation. So if I do a cross product, that's what I do. So I don't test on derivations in this class, I test on the use of things. So that is how you do a cross product right there. That's the formula. Now, if you're taking Math 254, you might have learned to do it in different ways. I actually had a very scary math teacher who taught me a certain way to do it, and I don't ever want to make him mad at me to this day, so I still do it his way, okay? So that's how he did it, okay? Now, you might have learned it differently. I've seen people here who put an extra I and a J column there and kind of do a cross kind of thing, which I can't ever remember quite how they do it, but what do? They kind of go like...
Just stack another one right next to it.
Yeah.
You go AX, AY, AZ.
And you do like diagonal lines?
And then you just do 4, 4, 4.
Yeah, okay. So you kind of go like that, like that, like that, and then you go the other way, right? Is that kind of the deal?
Something like that.
Yeah, okay. I don't remember that one. I don't learn it that way. But whatever, how you do it, I don't care, okay? You might have learned it in 254 to do it a certain way. I learned it when I took 254 to do it a certain way. I give you the formula right on the formula sheet. So I don't care how you do it, but it's, however you get it, just get it right. And you've got the formula right there if you need it. And it's on the formula sheet, right? Because before you take that midterm, you're going to look over that formula sheet. You're going to know where stuff is at, right? So you know how to use it and where it is. Okay? So there you go. That's a cross product. All right. Now I learned it with determinants, so I still kind of do it that way. All right. So what I have down there is a calculation on one of these. I'm on the next page. I'm on page 300. So if I'm going to cross A and B, I just use the formula. I'm going to get AXBZ minus AZBYI minus, that's a negative sign in there, AXBZ minus AZBXJ plus AXBY minus AYBX, and that's the K. That's how I combine things to get a cross product. So I give you an example there with numbers in it. So what I would do here, and the way I remember to do it, is if I want the I component, I cross off the top row and the first column, and then I cross multiply what's left. So that'll be minus 4 times 7, then minus 6 times 2, and that's the I component. Okay. The next step for me, and this is just how I learned it, I would cross off the top row and the middle column. This will get me the J. I take those out, I cross what's left, 3 times 7 minus 6 times a negative 5. I have to remember to subtract off the J component. And then the last one I do is I take out the last column and the top row, and I cross what's left, 3 times 2 minus negative 4 times negative 5. That's the K component. Work the numbers, and that's what I get right there. That's A cross B. Negative 40I minus 51J minus 14K. So that's pretty cool. Like I said, I have no idea why mathematicians came up with this thing. I don't really know why, but I know we can use it. Okay. So we're going to use it to calculate moments, and this is going to magically do all the stuff we were doing visually. It'll just kick it out for us. So what you do to get a moment about A is you cross R, which is a vector from A to the force, and you cross it with F. And if you do that, the 3D moment will automatically come out. Pretty good, huh? Okay. So that's how we use it. All right, now if you think about this, what we have here is a position vector from A, let's say, to the force. And then we take any vector from A to the force, and then we cross it with the force vector. By definition, the cross vector is normal to the plane about which the moment occurs. But so is the moment vector, if you remember that, when I showed you that earlier, which was a good bit earlier here, right there. The moment vector is normal to the plane in which the moment occurs. So there you go, that blue vector. Now the reason the numbers work out is, here's a 2D picture that helps to describe it. Sometimes I like 2D pictures because they're easier to see. Let's put a force in here and have it directed around A. Let's find the moment about A of this force. Let's take any vector that goes from A to the force, call that vector R, and then I have the force. Now what I'm going to do here, if I want to get the moment of that force about A, is I need a perpendicular moment arm. So to get that, I'm going to take the angle in between the two vectors and take the sine of that angle, and that will get me the opposite side here, which I'll call D. That is perpendicular from A to the force. So if the moment is F times D, what it is F times R sine theta. Well, that's the definition of the magnitude of a cross product. The magnitude of one vector times the magnitude of the other times the sine of the angle in between. Okay? So that will get me a nice moment vector there in 3D if I do that, all right? Just comes right out. Okay. So think of the moment as being a wheel and the moment vector as the axle of the wheel. Okay, so this cross product will just kick this stuff out. Okay, so if I'm twisting the lid off of that jar, the moment vector is normal to the twist, right there, okay? So let's just look at one here real quick. Let's put that force at C and let's figure out the moment vector. Let's not do it visually, and let's do it with a cross product. So this is page 310. The first part of it is exactly the same as I did before. I need to generate a force vector. There it is, negative 289, negative 506, and 144 newtons. Okay. What I'm going to do this time is I'm going to do a cross product. I'm going to calculate R, a position vector from A to C, and I'm going to cross it with the force. And that's all I got to do, and that will kick me out a 3D moment vector. So my vector from A to C then, that's how I'm going to put in my position vector from A to the force, will be RC 0.2 minus RA 0.402. So the vector from A to C is negative 0.400. So I took RC minus RA and I get RAC. It's negative 0.400. What I then do is I cross that with the force vector right there. So I'm going to cross negative 0.400 with negative 289, negative 506, 144. So what I'm going to do is take out the first column and the first row and cross what's left. I'm going to get 0 minus 0i. And then I'm going to cross off or take out the top row and the middle column, cross what's left. I'm going to get negative 0.4 times 144 minus 0. And then I'm going to do the last little bit there. I'm going to take out the top column and the top row and last column and cross what's left. Negative 0.4 times negative 506, then minus 0. I have a positive sign in front of the I component, a negative in front of the J, and a positive in front of the K. And I combine those numbers and I get the same moment vector as I got before when I did it visually. And if you notice, I combine the numbers in the exact same way. Okay? So the deal with this is if you don't like visualizing, and I don't recommend doing 3D moments visually because it's just too much chance for error, just run this cross at it, and they'll kick right out. Get a force vector, get a position vector, do the cross, and it just magically works. Okay? So that's how we do 3D moments. So do we have any questions on that? Kind of a mouthful there. We're not quite done yet, but we're almost there. Are we good with that? All right. So why don't I get you a couple of these to work on? So let's do 191, 192, and 193. Those are 2D moments. And why don't we do one 3D moment problem, I think. All right, let's do 201. Okay. And these will be due Monday. And Monday is the 27th, I think. Is that right? No, I'm not right about that. So today's Wednesday, the 20th. It is the 27th. Oh, okay. 27th? Okay. So there we go. So we'll get you those. Now, on this one, just when you run through this, use the example we just went through. Put it down on your desk. Use that to chart through how to work through toolbar. Okay? All right, so we'll call it good. Good.